Thank you for the invitation. I'll speak about a joint work with Manfred Lehn, Christoph Sorger, and Duco von Straten. And well, unfortunately, it doesn't contribute too much to birational geometry, but we start with Y P5, a cubic fourfold, and well, I mean, these are very interesting objects, and there is some interesting questions about the birational geometry of these. For example, there exists Y, which is rational. I mean, this won't play too much of a role in the talk, but just to make maybe a link, I guess this is one of the very few birational maps that you will see. I mean, the big question is, of course, are all of them rational? And I mean, we suppose that it's not the case, but it's unknown. And so there is the property that is important to this talk will be rather that these cubic fourfolds behave somewhat like K3 surfaces. And for example, you can look at the Hodge diamond of Y, and then inside this Hodge diamond you find in fact the Hodge diamond of a K3 surface with a small exception. I mean, that's that the H22 of Y is the H11 of the K3 surface plus 1. So, but still, in some sense, they behave like K3 surfaces, and this is why I mean, some of the philosophical reason why they can be used to construct symplectic manifolds. And so what we do is that we look at moduli spaces of rational curves on cubic fourfolds. So let me denote by RD the space of rational curves in Y of degree D. And to be precise, I want to think of this as being a subset of the Hilbert scheme, Hilbert polynomial d times t plus 1 of Y. And well, I mean, in general, for example, if you look at d equal 2, then you study conics, and they can degenerate in like 2 lines. So what we want to do is look at the closure of this space. And then the interesting remark is that if you look at the universal curve over it, it maps to Y, so PQ. And as I explained, there is the H1 of omega 3 of Y, which is generated by some form omega. And then we put sigma d. This will be the pullback along P of omega. And then we push forward, we integrate along the fibers, the map Q. So this gives us now a form of type 2,0 on RD. So there's a canonical 2 form, holomorphic 2 form on the space of rational curves. And the question I'd like to pose is Rd sigma d a symplectic manifold? And so, I mean, there's a result which motivates this, an old theorem of Bourvil, Donaghy, which says that if y is smooth, then the R1 space of lines, which then is obviously contained in the Grassmannian of 2,6. R1 is an irreducible symplectic fourfold. It is the formation equivalent to a Hilbert scheme of 2 points on a Cauchy surface. Irreducible, this just means that the H0 of omega 2 is one-dimensional. So these are deformation equivalent to the Hilbert scheme, and they come in a maximal algebraic family. I mean, this means that, well, maximal, so this means that the dimension of the deformation space of R1 is equal to 21, because it's a Hilbert scheme. And then inside you have spaces R1 of Y, which are a 20-dimensional subfamily. And I mean, this is the maximum that you can have, because in the space of all deformations of R1, the general element will be non-algebraic. So this algebraicity condition here is what needs at least one dimension, and so you cannot have more than a 20-dimensional family. And 20 comes obviously from the moduli that our cubic has. Well, but then you can look at d equal 2, and if I tell you that the dimension of Rd is equal to 3d plus 1, then it's obviously a rather naive question to ask whether it's symplectic manifold. And here is what happens in d equal 2. So if you take a general element of R2, which would be conic, this means that I mean, if I look at the projective space, which is generated by this Q in P5, this will be isomorphic to P2. And now suppose that Y doesn't contain a plane. If Y doesn't contain a plane, then we can look at the intersection with this P2, right? And we know that it already contains the conic. I mean, this is a degree 3 curve in P2. Contains already a degree 2 curve, so there's one residual line, and that's already all of it. So you obtain a map, in fact, to R1 mapping Q to the line LQ. And then if you think a little about this map, you see that it's a P3 fibration. So in particular, I mean, another reason that shows that it cannot be symplectic. And sigma 2 is the pi upper star of sigma 1. So this doesn't give a symplectic manifold, but that's sort of the pessimist way of looking at it, right? Because we can also say we start with something which has a holomorphic two form, and well, it's not symplectic, but this two form has some directions along which it degenerates, and we can contract these directions to end up with something symplectic. So, and this is exactly what happens to be our theorem. in D equals 3. So if y is smooth and does not contain a plane, then the space R3 is smooth, and there are morphisms R3 to spaces for Z prime and Z. Another morphism from the cubic that we started with. B is the following properties. So first of all, Z is irreducible symplectic of dimension 8. I is a Lagrangian embedding. What are the morphisms A and B? Well, A is a smooth P2 fibration. And, well, here is again a birational map, namely Z is isomorphic to the blow-up, Z prime is isomorphic to the blow-up of Z in Y, and B is just the projection map to Z. So this is another instance of constructing symplectic manifolds associated with cubic fourfolds. The symplectic two form is the one that I showed you. Or rather, I mean, if you have the P2 fibration, then it is clear that the two form that you have on R3 descends to a two form on Z prime, because I mean P2 doesn't have neither one nor two forms, so it's quite clear that two form comes from Z prime, and then it descends further as soon as you know that Z is smooth. It descends further to Z. So this is quite easy. The interesting question is how to construct the P2 fibration, and I will talk about this in a second. And for the moment, I would like to show you an element of the proof, which is quite funny. Namely, if you let's suppose we already constructed the space Z. So if you know that Z is symplectic and Y embeds into Z, then I'd like to show you how this implies that Z is irreducible symplectic. Namely, this goes as follows. If you assume not, right? So assume Z not irreducible symplectic. So then, by the Bogomolov decomposition theorem, you know that there is.
So you know that
we know even that it is trivial because I suppose that it's symplectic. I suppose that it's symplectic. I just want to talk about irreducibility. So by Bogomolov-Beauville, there exists a finite covering, finite étal, say k to 1, such that this decomposes as a product Z1 to Zm, where the Zi are either irreducible symplectic or they are symplectic tori. And moreover, because we already have a symplectic form, so I mean, Calabi-Yau do not have anything in 2-0, so this would spoil the. Yes, I mean, of course, as soon as Z is symplectic, also an étal cover will be symplectic. And well, for the same reason, I mean, for the reason that Y is simply connected, you have a lift to Z tilde. And then we will show that M is 1 and K is also 1. So because well, there exists one of the factors, obviously, such that Y to Zi is not constant. And then, because Y has become number 1, it has to be finite morphism. So we see that this Zi has to have dimension at least 4. But I mean, notice that in the theorem, the point is to show that I is an embedding, that Y embeds into the space. The Lagrangian property is trivial because it's just saying that, I mean, in Y there are no 2 forms, no holomorphic 2 forms, so there's no chance to be something else than Lagrangian. So it is finite. Let's call it phi.
Onto its image.
Finite. No. Finite onto its image. Yeah. Sorry. Sorry. Yes. Yes. Of course. And phi y is, I mean, by the same argument as before, is Lagrangian at a general point of phi y, the general point. So, I mean, This means it has to be already set tilde. So k m equal 1. And now k equal 1 follows from comparing the holomorphic Euler characteristic. So being irreducible symplectic, you know that this is 5. And it's also equal to k times.
Are you assuming dimension equality?
Yeah. I mean, okay, thanks. Thank you. So we have this, and we know that this is bigger or equal than k times 5, because we have the powers of the symplectic form. And well, it shows this part. Questions so far? Now, how to get the P2 vibration? Well, we'll use the following well-known fact, is that if we have such a curve in R3, then the projective space generated by it, P5, is always a P3. This implies that you have to show this. This is this comes basically out of the construction of the Hilbert scheme, where Piana and Schlesinger classify all these curves. So we have this. We have a map to the Grassmannian for 6, which sends a curve to its to the projective space that it spans. And now the basic question is the other way. What about what happens if we take the fiber? So we have a P3 in this P5, and we look at pi minus 1 of P, which we call the Hilbert scheme of generalized twisted cubics on SP. So where SP is the intersection of y with P. I mean, this is the fiber. This is a cubic surface. So generalized twisted cubics. I mean, twisted cubics. The smooth curves in this space are called twisted cubics, and generalized just want to have a word for, I mean, flat degenerations of that. So the question is, what does it look like? So these are now Hilbert schemes of twisted cubics on surfaces, and we analyze them for the different types of cubic surfaces that may occur. And so we ask for help of generalized twisted cubics on S for S. So the nicest case would be a smooth cubic surface. For some reason, we also put ADE singularities in this category. Or S could be S could be an elliptic cone that is we have a plane. In this plane, we have an elliptic curve, and S is just the cone over this curve over the vertex, say P. And surfaces can degenerate further to non-normal cubic surfaces, but still integral. And this is where this is already the worst degeneration, because I excluded that Y contains a plane. So cubic surface that is contained in Y will automatically be integral. And so I'd like to give an example. The easiest case, so for S smooth. For smooth, 50 minutes, right? For smooth cubic surfaces, you know that the pK of S is isomorphic to Z7. Look at the canonical divisor inside here. Take its orthogonal with respect to the intersection formulas. And inside, I look at, let's say, R of all classes with square equal to -2. And then it is known that R is R of E6 is the root system of the simple Lie algebra E6, which is a very funny geometric construction of that. And then one can show that C, a curve in the Hilbert scheme of generalized to cubics on S, corresponds to exactly to roots in this root system, and C will be an element of the linear system minus Ks plus alpha. Moreover, I mean this is just I mean you define alpha to be Ks plus C, and then it's just numerical calculation. So the moreover, we know that these linear systems, they are base point free, and in fact isomorphic to P2. I mean, this Z7 comes from the fact that S is a blow up of P2 in 6 points in general position, and these linear systems just give blow up maps, if you wish. And well, this lets us conclude that the Hilbert scheme, these kind of curves on S, is nothing else than union over all alpha in the root system minus Ks plus alpha, which is isomorphic. I mean, the cardinality of this root system is 72. So this is just the disjoint union of 72 P2s. Could maybe do this over there. So this is the P2 that we were looking for. So what it means is that the map from R3 to the Riemannian, once I factor out the P2, will be a finite 72 to 1 at a point corresponding to a smooth cubic surface. But unfortunately, this is not always the case. If S is an elliptic cone surface, this one, then I mean it's quite easy to show that. I mean how do curves in the generalized in the Hilbert scheme look like? I mean obviously they cannot map to an elliptic curve because they're rational curves. So you find that do I have colored chalks? So you find that they are unions of these surface lines, and to get the degree right, there's just 3 of them. So Hilb generalized twisted cubics in this case is nothing else than the symmetric product of the elliptic curve that we have here. Okay, which is obviously not a P2, but you can see the P2 by looking at the Albanese map. P2 is namely just the fiber of the Albanese map. But however, this example shows that it's somehow difficult to construct the P2 fibration abstractly by hand, and I should use some water. We cannot construct it by hand, and we need to do it well, somehow universally, because in fact we have such a modular space of curves for a cubic fourfold. Normally these curves are not too difficult to understand, but the thing that makes it really complicated is the cubic fourfold. So the idea to construct a P2 fibration is just to forget about the fourfold and do it and do it universally. So the point is that the space R3 has curves of 2 different types. So there's an open subset parametrizing curves which are arithmetically called Macaulay. And there is a divisor which corresponds to curves that are not arithmetically called Macaulay. And I mean, just to give an example, here the twisted cubic is something like this. But also other curves could be of type ACM. For example, it can degenerate into, it can break up in 3 lines, for example, which span a P3. On the other side here, certainly also know this sort of degeneration. It will degenerate to a plane curve of degree 3, but with a non-reduced structure, which comes out of the plane. So I mean, as I told you, it spans the P3. So so it spans the P3 infinitesimally, but it spans the P3. And in fact, these ACM curves are the ones that give the inspiration of how to construct the P2 vibration. And in some sense, these curves here, they are responsible for the birational contraction. Okay, and how does it work? I mean, we fix a P3 and consider a situation like this. We have a curve supposed to be of ACM type embedded in the cubic surface in some fixed P3. And then it is known that well, so without the surface, there exists a matrix A0, which is type 3 by 2, like this, and where the coefficients are linear forms on the projective space, such that the ideal of the curve in P3 is generated by the minors of this matrix, A0. Let me call it ideal associated with A0. And, well, call it U0. And then obviously there is a group action that comes into the game. So the group G0 is a GL3, GL2, which acts like conjugation on these matrices. And there's a C star which acts trivially. And then in fact, U0 modulo G0 in semi-stable points. This is just the Hilbert scheme of generalized twisted cubics on P3. I mean, after a blow up. This is the way how to construct the Hilbert scheme. And what we do is very much inspired by this construction. So what happens now if the cubic surface enters the game? Here I should say that this action preserves the ideal, not necessarily the minors themselves, but the ideal generated by them. And now if in this situation the cubic surface S is given by a zero set of the cubic polynomial, then, well, we can write G as sum of Li Mi, where the Li are certain linear forms. And this can be written as determinant of a matrix, namely the matrix A, which consists of A0 here, and then here I have to write L1 minus L2 and L3. this lives in 3 by 3 matrices with linear forms as coefficients. And again, here we have an action of a group, G, which is now GL3 by GL3, from the left and from the right. And this group leaves the determinant of G invariant. But not, well, if I denote, say, A0 from the point of view of A, I write A0 as the restriction of A, but not the ideal generated by the restriction of A. So because, I mean, obviously this mixes, so to say, these columns with this column, so I add something else in the ideal, which changes the ideal. So what we do is that we look at P. This is the parabolic subgroup leaving exactly this ideal invariant. And this is something like GL3 times parabolic subgroup of this GL3, which contains the GL2. Right? And this is the basic idea for the construction of the P2 federation. So as you see, this construction parallels the construction of the Hilbert scheme of these curves in P3. So what we can now look at is U semi-stable points modulo P. This maps to U semi-stable points modulo G. And we fixed a subspace of P5. So basically we can do this construction over the Grossmanian for 6. And here I want to write the projective space of 3W dual. So I mean W now is the universal rank 4 bundle over this Grossmanian. This is a bundle over it, and fiber-wise, these are the cubic surfaces. So these are cubic surfaces contained in PW. This is a bundle over it, but we also have a section of the bundle, right? This section is nothing else than a plane P descended to P intersect Y, the cubic surface that is cut out by the plane. So this is relative. I mean, this is just the determinant. And this is the projection. Now, by what I explained before, here, this space corresponds to curves and surfaces, such that the curve lies on the surface. And I explained to you that that this produces a matrix A, such that S is the determinant of A. Well, and then you go further with the determinant. Right? And now we look at the space R3, and then we have a map over here which sends a curve C just to C and S, which is the span of C intersect with Y. Well, and now you look at what happens here. I mean, here this is just a G modulo P bundle. P the parabolic subgroup, and this is the P2 that we were looking for. So well, then you do the obvious thing. You take the fiber product of this map, and you obtain your P2 fibration here. So this is how it comes about. And well, I have 2 more minutes, right? So in the remaining time, I could try to give you an idea where this birational contraction comes from. So if we have R3, and inside we have the divisor of non-ACM curves, then I told you how they look like. We know how they look like. Namely, there's a singular rational curve in the plane together with a tangent direction which comes out of the plane. So let me call this E. Let me call this singular point P. The whole thing is the curve C. And then a point inside here corresponds to, well, I should say P. Then I wanted to say E, but E is obviously nothing else than the intersection of the P2, which is generated by E, with the cubic fourfold, and somehow PC, so the free space generated by it. Then, moreover, you have to notice that the dimension, I mean the cubic surface S, which is Y intersect with PC, has to be singular at P, because I mean, if you look at the dimension of the tangent space of C and P, it's a tangent space of dimension 3, and this should be contained in the surface. So the surface has to be singular. But this means, on the other side, that if I rotate this plane, I will still cut out a non-ACM curve. And in fact, this is the P2 family. So there will be a divisor D prime. And the map just looks as like this. We map a curve, P, PE, and PC, just to P and PC. We forget about the PE. So now you see that by what I said here, it just means that PC has to be contained in the tangent bundle, in the projective tangent space of Y and P. So this is nothing else than the projectivization of the tangent bundle of Y. And then there's an obvious map to Y, the projection from the bundle. Well, and then the way that we construct Z is just as a contraction. So this is contraction of D prime along P. And this gives the embedding of Y and Z. Thank you very much.
Thank you very much for the talk. Other questions?
I'm not sure whether there's an answer to your question, but I mean, if you can show that so the Hodge structure of the cubic fourfold embeds to the Hodge structure of the manifold Z. So I mean, some special loci in the moduli of Z correspond to special loci in the moduli of cubic fourfolds. But, well, I don't know if this.
So I mean, when I see a P2 vibration of a symplectic eightfold, that looks like a subvariety of a symplectic twelvefold.
Beg your pardon?
I mean, a P2 vibration of a symplectic eightfold looks like a subvariety of a symplectic twelvefold. Is there any hope to guess what it is?
Well, good question. I mean, could be symplectic 12-fold. No, sorry, for 12 I have no idea. I would have said something was 10, but no, this doesn't make sense. Good question. No, sorry. I mean, of course, you can try to play around with higher dimensional, with higher degree moduli spaces, and like for example, if you take degree 4, then you might look at the locus where the curve breaks up into a line, and one of the curves that we parameterize in R3. So, but I mean, this probably won't give an embedding, rather a sort of correspondence. No. Y is smooth and doesn't contain a P2, yeah. So
here you realize Y as the Lagrange orthogonal.
yes. Yes.
It's true that if it contains P2, then you cannot realize.
Well, I mean, if it contains a P2, then already we do not succeed to construct the space Z, because yes. Yes. I don't think so, and I guess Nick is a better. Okay. Okay. But I mean, no, I don't. I mean, probably it should embed everywhere. I mean, that's what comes out from your local analysis? Or? Okay. I mean, they constructed some of the embedding locally of the cubic fourfold. So there don't seem to be obstructions to fourfolds containing plane.
Do you see this rank 3 vector bundle such that on Z prime giving this P2 vibration? They have geometric construction.
I'm not sure whether there is a rank 3 vector bundle. I mean, it could be that you only have a multi-section, and I mean, you would need to have a section, right? In this case, and I don't know where it comes from, where it should come from.
This is talk about the deformation influence class
Ah.
What's the guess, or what was the result?
It is, from my part, it's a guess that it's deformation of the Hilbert scheme of 4 points, and I think from Nick's part, it's a theorem. Okay. No, I mean I mean we can tell you about the Euler characteristic, topological Euler, which coincides with the Hilbert scheme of 4 points. and there are some of three natural candidates where you can look for. Candidates of special cubic fourfolds Y, such that you could succeed to at least construct a birational map. This is containing a plane or a singular A1 singularity at one point, or Pfaffians. And I think in all the three situations there are approaches to it which seem promising. But don't ask me.